Hello and welcome to my report on the Week 11 readings, Applications of Faraday's Law. This week we looked at some applications of Faraday's Law which we've been looking at in lecture recently. We saw how we can use a wire coil to generate a magnetic field and a current in another coil, the difference between a solenoid and a coil, applying Faraday's Law to a solenoid, and lastly, motional EMFs. Both Faraday's Law and the formulas used for the magnetic fields were familiar to me from earlier in the course. We also briefly touched on how Lenz's law can be used to determine the direction of magnetic fields, which we've seen before in lecture. First, we saw that the EMF of a coil is the number of loops times the change in flux over time. We then looked at how a current-carrying coil can be the source of magnetic fields and current in another coil. We can use the right-hand rule to determine the direction of the magnetic field. By connecting a coil to a source of EMF, it will produce a magnetic field, and if we place a second coil in that field, then a current will be generated in the coil. We worked through an example of this in the video. Then, we looked at Faraday's law with respect to solenoids. The first thing we did was to define the difference between a coil and a solenoid. Both are many loops of wire, but the difference is to do with the ratio of length to the radius of the loop. A collection of loops is a coil when the radius is greater than, or roughly equal to, the length of the object. It would be a solenoid if the radius was much smaller than the length. We also saw that the magnetic field in a solenoid is constant and has a magnitude of mu0 times the number of loops times the current, all divided by the length of the solenoid. The magnetic field due to a solenoid is 0 when the observation location is just outside of it. We then worked through an example of placing a solenoid inside a current-carrying loop and calculating the induced current. In the last video, we looked at motional EMFs for the first time. These are EMFs which are induced on a loop when the magnetic field is constant. Seeing as how the magnetic flux is equal to the magnetic field times the area of the loop, and there is a change in flux over time, we know it can't be due to the change in magnetic field. Instead, it's due to a change in area. We saw this happening in one of two ways. The first is changing the size of the loop by creating a U-shape of wire and placing a rod to make contact with both prongs. We can then place this U-shape into the magnetic field and move the rod up the wire to change the size of the loop. The other way to do this is by placing a loop in a constant magnetic field and rotating it. This will change the size of the loop, which is able to interact with the magnetic field. Motional EMF was by far the most challenging topic for me this week, but after having read the Motional EMF physics book page, I feel I understand this a lot better. And thinking about these topics in the context of my major, computer science, I'm particularly interested in how motional EMFs are used to generate current. I'll be interested in learning more about how generators work. This concludes my report on the Week 11 readings. Thank you for listening.